Okay. Trying to see all the things that I need to see here. It's like virtually running from lecture hall to lecture hall. I just got done doing the watch party, and now I'm trying to make the live stream work. It's me running down the virtual hall. For those of you who aren't visiting the watch party, you should check it out. We have it on Tuesdays and Thursdays before this lecture. It's from 10 to 12. It's featuring me and this same content. But we have a chance to do some more conversational stuff there. So, all right. I think everything is set up and I'm ready to go. So today we're going to talk backtracking and branch and bound. We mentioned them when we were in the algorithm families lecture. Now we're going to go in depth and start to get some real background for the way that we can use branch and bound to help us solve the TSP. And I still can't see chat in case anything goes wrong. Okay, that's there. Bring that up. Bring that up. All right, now I can see it. I can see it. Okay, so we'll talk about constraint satisfaction, of course, and we'll make sure that we understand what that is, and then we'll talk about how we can extend that with optimization. Those things are fundamental to understand here because we've seen how backtracking and branch and bound rely on both of those things. We'll look at backtracking first and see sort of a general form. We'll see the things that need to be included in a backtracking solution, and it's possible to sort of reorganize them sometimes, but all of the elements have to be there. We'll also look at a specific backtracking problem, which has some source code. If you want to grab that source code now, it's the nqueens thing, and you can, I think it's accessible through the files in Canvas. I'll show you how to pull that down later, though, when I'm in the demo. And then we'll talk about branch and bound, and specifically the traveling salesperson problem. Look at that. I apologize for the nose running thing. It's just not going to stop, so I'll be sniffling all through this lecture. It's pretty heinous, but I can't do anything but let it run. Backtracking. So we know that backtracking can be used to solve constraint satisfaction problems. And these are problems where we're forced with a set of rules and a general outcome. And the question is, can we get to the outcome without having violated any of the rules? For instance, how about map coloring, graph coloring? Is there a way that I can color all of these vertices or states without having anything adjacent? So my constraints are I've got 4 colors. My constraints are here's the graph. My constraints are no 2 adjacent vertices can be the same color. There's my constraints. If you can find a way to do it, that is a solution. Oftentimes these have more than one solution, and you can think pretty easily of, even if there's only one way to color a particular map with 4 colors, you could easily just cycle those colors and make the reds red and the blues, the reds blue and the blues red, and that would give you a different map coloring, even though it's not realistically unique. But there is the possibility of more than one solution in many of these constraint satisfaction problems. Some examples, of course, sorting. That's a constraint satisfaction problem. Can you put all of these items in a container such that no item is larger than the items that follow it? That is a constraint that must be satisfied, which is why sorting is actually a constraint satisfaction problem. Many puzzles, Sudoku, I'm just non-stop with number puzzles on my phone. That's my my soothing, is I always am doing some number puzzles. If anybody's, if I've got to wait in line or I'm just bored, I just pop them up and thumbs ablazing there. So I love those things. The GRE has the analytical section on it as well, which is doing a lot of these constraint satisfaction problems back when people used to take entrance exams. Thank you, COVID. Constraint satisfaction problems will go over all the possible solutions. And then it will check to see if that input combination satisfies all the constraints. Usually we can stop when we found a solution. Sometimes it's a little bit harder to write it in a way that it does that, but we'll have a chance to look at the general form and you'll see that. Down below you see we've got optimization grayed out. That's in the second half when we get to branch and bound. Same sort of thing. Constraint satisfaction problems can rely on backtracking algorithms. There are better ways to do sorting, for instance. All of the sorting algorithms that we've given you were not backtracking algorithms because there's a better way to do it. However, if I was unable to come up with any of those sorting algorithms, I could write a backtracking algorithm that said, well, let's try this one here, and let's try this one there, and then try the next one. Oh, there's a constraint failure, so then I'll try something else there. And so you could solve the problem of sorting with backtracking. But there is, that's what I'm saying is the constraint satisfaction problems can rely on backtracking algorithms if there's nothing better. So this constraint satisfaction problem that we saw is with backtracking is asymptotically as bad as branch and bound. It's as bad as brute force because it does try everything systematically. But if there's something more sophisticated, then you would definitely use that. Here's one general form of backtracking. We start out with this function called checkNode. Last line, checkNode calls checkNode. So it's recursive. And what we're doing with this node V is we're picking one of the places that we have to color. Or later when we start working with this n queens problem, we have to place n queens on a board. This is the first queen or the second queen. This value here is how far into the solution are we? So every time I do a recursive call, I'm calling it deeper into the solution. So if I'm coloring 10 states, I may have called this, here at 8 states already colored. Then when I call again here, this is with 9 states colored. That's how we advance the solution. We've also got to have, with every recursive function, we've got to have some base case, some way to get out. So we'll see that happens up here first. We've got this if promising check. And if promising says, hey, we've just put together a possible solution. Promising checks to see, has that partial solution or complete solution, has that violated any constraints? Because if it's a partial solution and I violated a constraint, I might as well stop. I'm never going to get to a real complete solution with a violated constraint in there. So this lets me get out, right? It also, if I've got a solution, you see here, if it's promising and solution of V, meaning if the V node is one that completes my solution, then I'm also done. I don't try to extend the solution. So here in this inner if, that's handling what to do when I have a solution. The inner else deals with extending the solution. And then promising says, well, we've got something that's working or not. Should we continue to extend it? So those are my 3 primary elements: a solution check, a promising check, and a way to extend my solution. What makes these really hard to get to is it's already hard enough to understand recursion. CheckNode calls CheckNode, calls CheckNode. Can't define CheckNode unless we have CheckNode. But we would need CheckNode to define CheckNode, and that's recursion. Hard enough. But look at that. Recursion, it's inside a for loop. So we've got iteration built into this recursion. And so every time when we get to a checkNode call, the first thing we do is come up here and check to see if it's promising. If that fails, checkNode returns instantly, and we're inside of a for loop already, still trying to do more work. Every time except the very first call. The very first call obviously is not called from within a loop. It's called from wherever you set the problem up as. But when that one exits, we know we're done with whatever solutions we did or did not find. But keep in mind that you have to manage this for loop with the recursion inside of it. That's fundamental to backtracking. It's fundamental to branch and bound, which is just an extension of backtracking, which therefore makes it fundamental to the way that we solve the traveling salesperson problem in Project 4C. So you have to get this. That's what I'm saying. So this is a general form, and later on we'll look at what does a function like promising mean, or what does a solution check mean, because this general structure works for all backtracking problems. The only thing that makes one backtracking problem different from the next is, how do I calculate if a partial solution is promising? How do I calculate if it is a solution? Those are the problem-specific things that you have to add. And then how do I reliably extend what I have? Those are the three things that are sort of unique, but they're building block pieces that get plugged in here. Here's another version of it. This is an alternate form. You'll see though, we've got those same things. I've got a for loop that calls check node inside of it. That's used to extend my solution. I've got a check to see if this is a solution. That's a solution check. And I've also got this promising check that says, hey, if what I've got partially is going to work, then I'm going to extend the solution. So you see that the check node call is where we go deeper in to the search tree. That's extending the solution. If it's not promising, then I don't go in. If it is promising, I do. That's what's going on there. And that was the same thing I saw here, right? Because before I'd say, let's go in, and then the very next thing that I did after going in was check to see if it was promising. Here, this version sort of inverts that. So it says, well, let's check it first, and then we know we can extend, right? The other one says, well, let's try to extend it and then check it and see if it works. Either way, this is going to work. So you'll look at different backtracking solutions, and some of them might use this format, some of them might use the previous format. We've got here our early base case. If this is a solution, write it as a solution. Otherwise, try to extend the solution. And I only extend it if it looks promising. I'm looking through all my options that I can to extend the solution. Anything that works gets a shot. So this is another way to write backtracking. This is one that's going to be probably closer to how you do Project 4. So in my general form of backtracking, I mentioned I had these three things that were important. Solution of V. Is this the right thing? Oftentimes this is fairly simple. So if you're doing graph coloring, and you know you're coloring 15 states, solution of V is like return V equals 15, right? If V is not 15, then we don't have a solution. If V is 15, then we have a solution. Often solution check is fairly easy because you're just trying to see if you've gotten enough work done. Promising is the one that's really the hard work. How do I come up with something that I know that I can check this partial solution and see whether or not it's violated a constraint? It's easy enough to do brute force. I can always check to see everything works. But what I need to do is, because this thing has this exponential brute force complexity, what I need to do is I need to be doing these promising checks as efficiently as possible. I can't spend a whole lot of time in promising. I can't do a lot of work in promising because promising may be called exponential or factorial times. We'll see that it gets called factorial times in Gen Perms, which we use in Project 4C. So we want promising to be quick. And then check node, of course, is the overall function. We'll call that. So we're going to do this example with n queens. And n queens is a small logic game where you take a chessboard that's n by n size, and the question is, can you place n queens on there that don't threaten each other? Meaning I can't have two queens in the same row because that queen could attack that queen. Queens, if you don't do chess, have an unlimited movement amount horizontally, vertically, and diagonally. So that's why we're trying to see the difficulty of placing queens on this board is any queen here completely dominates its entire column and its entire row, plus one or more diagonals. So, starting out small with a 1 by 1 board and one queen, can I do it? Obviously, that's trivial. There's no other queens to be threatened by or to threaten. How about 2 by 2? Well, now this is impossible. They're either in the same row, they're in the same column. Let's try that again. They're either in the same row, the same column, or on the same diagonal. There's no way to get around it. How about 3? Similar to 2, not a lot better there. They're either going to be more than one of them in the same row. I got my hands backwards today. More than one in the same row, more than one in the same column, or more than one in the same diagonal. However, at n equals 4, we get to a place where we can get a solution there. I'll show you what one looks like, and then we'll work on how to find one. But it turns out that after n equals 4, I don't know if there's been proof that anything above n equals 4 can't be done. I think they all can be done. Like I said, this is not an easy problem to solve. This one ends up being what's known as NP complete. So we don't have NP hard problem. See, so we know that there's no polynomial solution to this, but we can in polynomial time, if somebody gives me a solution, I can in polynomial time check to see if it is a solution. So these problems are really hard to do. They make some of our most fun CS work though. So here's what n queens looks like when I use just a normal chessboard. And you can do this at home if you feel like it. If you've got a chessboard, pull it out there, and obviously your chess set won't have n queens or 8 queens, but you will have pawns, and you just make the pawns act like queens. Allow them to attack all the way across, all the way down, and all the way diagonally. If you take your standard chessboard and try to put these 8 pieces on there, you'll see that brute force, sort of like monkey queens, if you will, monkey queens would check 1.7 times 10 to the 14th. That's a really large number, right? I'm going to go with something like 100 trillion different possibilities. And that's a lot of monkeys. I don't even think one monkey could pull that off in a lifetime. And many of these are ridiculous. So you would try, like, what if I've got all the queens in the first row? Well, you know that wouldn't work when I had 2 queens in the first row. Why would you try 3 queens or 4 queens or 5 queens? But brute force, we know, tries it all, whether it makes sense or not. If we make this a little bit sensible, to just sort of prune the search space in general, let's do something reasonable. Say, well, I'm going to place these in there 1 row at a time. And since I only place 1 in each row, hey, there's one of my constraints satisfied. That is, nobody in the same row, nobody in the same column, nobody in the same diagonals. Well, if I only put 1 in each row, there's 1 constraint I don't have to check for. If I do that, I still end up with these 16.7 plus million different possible ways that I can put these things on the board where there's only 1 in each of the 8 rows. There's still some that are doubled up in columns and diagonals and whatnot, but 16 million different ways to do it, and then there ends up being actually 92 solutions. So that's pretty interesting. That's still a fairly large search space. How can we further reduce the search space? That's a good question. Let's take a look at backtracking and see how it works. We'll start here and place our first queen, and this is just a 4x4, and you can see how to extend this and do so on your own. But we start out at a 4x4, and I place a queen in the first row. What goes on next? Well, that's great. I put a queen in, no problems. I would say this is a promising looking partial solution because no queens are threatened. All right? And by the way, when we get done with this whole video, I'll run the disclaimer that says no queens were harmed during the filming of this video. All right, next step, right? We can see that as I try to place something in the second row, that first column is threatened by the queen in the first row. The second column is threatened as well. So I don't even place them there. Well, actually the algorithm tries it and says, oh, these are a threat, so that's not promising. Moves it to the next place, that's a threat, not promising. Then it puts something here. And now we've got a promising partial solution because there's 2 queens on there in the 2 rows, and neither of them threaten each other. If you check their horizontals and diagonals and verticals, they're all clear. Great. What happens on the next row? I can see that that first position is definitely threatened. Turns out that that second row item ends up threatening all of the other positions in the third row. So I would try each of them, find that try each of them, and find that they violated a constraint. There's the V word. Jeez, Pete. All right. I try each of them and see that a constraint gets violated. Then I backtrack and try the next one. I try the next one, and try the next one, and try the next one. Once all 4 of them have been tried, I say, well, there's nothing I can do here. There's nothing promising in row 3 with the current state of the world, so let's backtrack again. I'll backtrack to row 2. When I do that, I say, well, there's one more thing I haven't yet tried in row 2. That looks good. So now let's move forward again. I'll see that that first one still always is going to threaten that entire first column, but now that second column is available. So I'll try that. It looks good. That's a good one, right? Because there's 3 items placed, 3 separate rows, 0 threats. This is a promising partial solution. However, it's all fails after that. There's no way that I can put that anything in that 4th row. And in the slide before this, it's slightly out of order. You saw that when I try to backtrack here into the 3rd row, let's try to backtrack into the 3rd row and place the 3rd row into a different column. And that queen, as it moves over, gets into a threat from the 2nd row, and then another threat from the 2nd row. And so then I backtrack again. I can't do the 2nd row any other way because I've already tried all 4 of them with that current 1st row. So then I backtrack again, and I get to, let's change the 1st row because that seems to be locking us down. We end up backtracking all the way back to row 1. We'll show you some more of that in a bit. But remember, this is our constraint satisfaction of n queens. We could require 1 solution. We could require several solutions. We could require all the solutions. In general, backtracking just needs to find out if there is a solution that exists. And then if you write it in such a way that it will deliver that solution to you, that's optional as well. So here is our generic backtracking with the focus of n queens placed on there. We're going to see how we can write solution, how do we write check node, and how do we write promising. Solution is easy. I mentioned that one earlier. In a lot of these, you say, well, I've got to place n queens. If I haven't placed n of them, this ain't a solution. So I'll check the depth of my solution. Remember that backtracking, we call that a depth first search. We're trying to see, can I place one in the 1st row? Can I place one in the 2nd row? Can I place one in the 3rd row? Place one in the 4th row. Oh, that's a fail. I'll go back up to the 3rd, move over a bit, come down the 3rd to the 4th to the 5th. If I get all the way down to the bottom, I've placed all 8 queens. There's my solution. So solution is just literally, is depth equal to n? Perfect. Check node, that's pretty straightforward. We're just going to do the thing that we've set up. We're going to call, if I've got something that's promising and partial, and then it's not a solution, I'm going to keep calling it. Otherwise, if it's a full solution, I'm going to print it and not call check node any further. Or if it's a failed solution, then I'm going to not call check node to evaluate any further. Here's promising. As I mentioned, this is always the heart of your backtracking problems. And this one is going to be fairly tricky as well. We talked about promising. We know that we can't threaten in a row, can't threaten in a column, can't threaten in a diagonal. How can I do that quickly? The naive way is to say, well, I just tried putting something in this column. I'll check all the other columns to see, all the other rows of this column to see if I've got a piece there. That makes it linear. Then I got to check all the diagonals this way. I got to check all the diagonals this way to see if I've got a constraint violation. That's too much linear work. I want something faster. And so the way that we're going to do this is, instead of doing this check on a 2D board, and this is a 2D problem, I'm not lying, it's a 2D problem, but I'm not going to look at it in terms of my 2D partial solution. I'm going to do this with some 1D vectors, or arrays, however you want to talk about it. I'm going to have one that keeps track of column availability, meaning, is this column available? Has there already been a queen placed here? If there is, then this column is not available. Perfect. Same thing with left and right diagonals. I'm going to say, well, if this diagonal has not already been occupied, then it's available. I can place a queen there, and I can check the other diagonal. If that other diagonal is okay, then that place right in the middle, okay. So this is good. We'll figure out how these X and Y things work in terms of the diagonals in a bit, but this is what we're going to do, and I'll walk you through it. For 4 queens, we know that my entire tree has 256 leaves, right? That's 4 decisions for the 1st row, times 4 decisions for the 2nd row, 16, times 4 decisions for the 3rd row, 64, times 4 for the 4th row, 256. When I do backtracking, I can investigate 19 branches and find a solution. That's pretty impressive. Out of those 256 leaves at the bottom of my decision tree, I only have to look down 19 different branches before I find a solution. That's less than 10%, right? It's pretty nice. We look at promising, leading us toward a solution. Not promising will never get us to a solution, so we prune. Let's count these branches. And this is a simplified way to do this. You see I've got this chessboard here, and it's my 4x4. And what I'm going to do is just label these things A, B, C, D, E, so we don't have to talk about row and column. So each one of these has a unique one. It works because I'm in 4x4 and I can uniquely identify them. So I'll start out my search. right? There's a queen in the first one. So my branch search then is A. As I try A to E, I see a vertical threat. So I try something new. A to F gives me a diagonal threat. That's my second branch investigated. And both of those lead to prunings. I don't have to worry about how many different ways after each one of these fails are there, right? If I kept AE, there's 16 different ways I can do these last two rows. So pruning AE cuts 16 things out. Pruning AF cuts 16 more out. Remember, there's 256. So those two prunes right there have already gotten rid of 32 of my 256. So I've already taken out 1/8 of my entire search space just trying to place that second queen in 2 places. That's great. I've cut out 12.5% of the work, and I got some pruning to go. So at AG, that shows no threat, so I keep it. Let's try I after the G. There's a vertical threat there, gets pruned. A to G to J, that is a diagonal threat, so that's not going to work. I'm going to prune that. A to G to K, that's a vertical threat. It's also a diagonal threat from A, so I'm going to prune that one either way. A to G to L, now I've got another diagonal threat from G to L, and I'm out of things at the end of this branch. So now I'm going to prune AG and go to AH. AH is valid. AHI, though, shows up with this vertical threat that I don't like. So I've got these bold ones in there where I'm extending the solution, right? So AHI is a vertical threat. AHJ looks good. There's no threat there. AHJM has my vertical and diagonal threats. AHJN has my vertical and diagonal threats from rows 3 and 2. We see these threats work me all the way across the bottom. What do I do next? I'm going to backtrack here. I try to put K in there, that third column, third row. It's threatened by both the first and second rows. And I go to the fourth column in the third row, and that's threatened by the fourth column in the second row. So now I've hit the end of my third row rope, if you will, and I've also hit the end of my second row rope. So I'm going to backtrack, but I've got to backtrack all the way up to that first row. This moves the queen in the first row to the second column there, puts it in B, and I start filling things in. B to E is a diagonal threat. B to F is a vertical threat. B to G is a diagonal threat. B to H, we got something here. Something we can extend, because now B and H don't threaten each other, so I can place something at I. And look at that. I is unthreatened as well. No horizontal, vertical, or diagonal threats. So let's go to the next row. B, H, I, and M. There's my trip down this branch until I violated a constraint. I is directly above M, so I prune. I move over one. N is directly below B. It's diagonal from I. It's diagonal from H. It's got all the threats. Out. Then I place one at O. This is my 19th branch investigation. Most of them had failures. Otherwise, this is me getting down to the depth of 4 chosen queens. So there's my solution. That is a 4 queens solution for backtracking. And putting it into 5 queens or 6 queens or 8 queens and beyond, you do the same thing. This exact same way works. So as I look at my search tree, I say, well, I've got these 4 decisions that I can make at the first level. This is me picking one of these, picking queen 1 in one of these 4 columns. Great. At the second decision, I've got to choose to place queen 2 in one of those 4 columns. And we can see that if queen 1 is in the first column and queen 2 is in the first column, I've got a constraint violation, right? There's my constraint violation. That tells me I can't put anything there because queen 1 and queen 2, they're already violating things. So I've saved these 4 things below that, and then there's 4 more below each of them, so 16 of them got pruned off. And this is how I get my savings with this search tree here. All right? You'll see that the one that we actually found comes through here. One of the ways I can get there. So I go to column 3 in the first row, then I go to column 1 in the second row, is it possible for me to get down to the bottom without violating a constraint? There's 64 branches at this level. I just want to get one that punches me through. And there I find it, right? So column 3 in the first row, column 1 in the second row, column 4 in the third row, and all I need to do is get down to the bottom, right? These 256 leaves, some of them are my solutions. All right, you see that there. And where do I place it? In that second column of the fourth row. And this is similar to the solution we saw when we saw the BHIO. This is the mirrored version of it. So it's flipped over its horizontal axis or vertical axis. It doesn't matter. They're kind of symmetric. All right. So here's my backtracking summary. It allows me to prune these branches that aren't promising. All my backtracking algorithms have this similar form, or at least these similar 3 elements that we can sort of move around depending on how we want to write things. So we've got, is the solution, is this promising, and how do I extend the solution? Often the hardest thing to come up with is, how do I write promising? So I'll show you how we did N queens when we get to this N queens demo, right? So let's talk branch and bound first. We'll talk branch and bound, and I need power for the laptop. We'll talk branch and bound, and then we'll do the N queens demo at the end. I think that sounds reasonable. I don't want to run out of time while we're doing demo, because we did a demo when we could be talking about content. All right, so up next, branch and bound. Branch and bound now, as we talked about using backtracking to solve these constraint satisfaction problems, branch and bound is used to solve optimization problems where we also have constraints involved. So as before, we had this stuff when we were just talking constraint. Now we're talking optimization. So we still have to satisfy all the constraints, but now we're going to be trying to minimize some objective function. Something really simple as we talk about traveling salesperson problem. Can I find a path? Certainly you can. The question is, can I find a path that's the shortest one? That's the optimization. All right? So these optimization problems are similar, except we have to calculate this objective function every time we get a solution. Say, well, is this a solution? And then how does this solution compare to the solution that I already have? Because if it's not better, then it's no good. But if it is better, then I'd like to keep track of that. This is why I can't stop early. I can't just say, well, I found one, we're done, and it's optimal. You can't do that. You're going to have to check the next one to see, well, maybe the next one's better, or maybe the one after that's better, or maybe 15 other solutions down the line, I find something even better still. So we can leave early with constraint satisfaction problems because usually the answer is, the question is, can I find one? Optimization says, can I find the absolute best? So just as before we talked about sorting and constraint satisfaction, optimization problems often have more, sophisticated ways to do them, but if you can't come up with that really cool sophisticated way, you can always fall back on branch and bound. So we'll call branch and bound B&B for short. And what we're going to do is extend backtracking to optimization. So we're going to take this useful property here. We're trying to see if we can do some minimizing with it, right? So we end up with what amounts to another constraint. So I've got all the rules of whatever my current problem is. I can't have this touching that, or I can't have more than one of these in this area, blah, blah, blah. Whatever my constraints are, those are already there. But when I'm trying to do optimization, I get to add another constraint. And this one is controlled by me. And so what I do is I say, well, I've got a solution. I've got one solution. And what I'm going to do now is, as I try to find the next solution, is before I get the solution done, I have part of a solution. And when I've got a partial solution, my backtracking says, well, let's try something new. If it doesn't violate a constraint, extend. What I'm going to add to that promising check is, let's try something new. If it looks like it's going to be too expensive, prune that as well. It's a new constraint that I can violate, right? So for instance, let's say I've tried to find some short way to get to point B. I'm at point A. So to get to point B, I've already got one path that gets me there in 40. Let's say I've tried some other partial path, and partway down the path, I've already traveled 50, and I'm not even done yet. Well, that's a fail, right? My best is already 40, and if I'm currently working at more than 40, I would definitely give that up. Even reasonable people would do that, right? It gets a little better, though, if I say, well, I've walked halfway along this path. Can I estimate how much work is left? Because if I've walked 20 and my estimate is, well, there's still another 30 to go, I don't need to walk those 30 to figure out it's not better than my 40, right? So that's what branch and bound does. It allows us to add one more constraint that says, let's look at what we've got, and if it looks like it's going to save me, then I'll try to further investigate it. If it looks like it's not going to be good, I've got a new way to prune, and we know that the more we prune, the faster we get out of this. So this is great. We end up dropping partial solutions that aren't better than our best. So here's what a general form of branch and bound might look like, and you can see that it's fairly similar to backtracking. Remember, we said we were going to extend it. What have we done here, right? I've got this if promising here, I've got an if solution, and I've got a way to extend the solution. It's great. Promising now has two parameters though. So we're just looking at a current version, that's what the V says. What is this vertex promising in this particular state? Also, I'm going to add current best as well. So now the promising has access, and you might not pass this in as an actual function parameter. If you write this in a class, you can have the current best stored as a member variable so that you don't have to pass it. But either way, promising needs to have access to the best because promising now does more work. It now checks to see if it violates any constraints, and it checks to see if what you've done so far looks like it's going to lead us to an optimal solution. If it's not going to lead us to an optimal solution, promising still says no, even if constraints aren't violated. Other than that, this is basic backtracking. Same thing as we looked at before. The solution is, have we gotten deep enough? Have we done enough node coloring? Have we visited enough cities? Have we put enough things in our bag? Whatever the problem is, solution is usually easy to figure out. Update. Now, where did update come from? Let's look back there. See that I've added that inside this if statement here. If I've got a solution, then I might need to update my current best, right? Because when I've got something that's promising and it's a solution, right? Promising means it hasn't violated any constraints and it doesn't cost as much or more than what I've already seen. So if it doesn't cost as much or more of what I've already seen and it's a solution, then that's actually my new best. So this update of the current best is how I keep track of my current best. And this is often where I need to make a copy of my results. I know we're copy shy, hopefully you should be. But this is a place where I need to make a copy, right? Because here what I'm saying is I've found something that might be the best. If someone wants to ask me for this later, I need to be able to produce it. So this is where this update comes in here. You're going to have to do something to keep track of it. If you've got some new solution that's better than your current best, then we need to, at the very least, update the value of what current best is. How much is current best? We might also need to copy the exact way that we got to current best as well, depending on what you need to deliver. Sometimes an optimization problem might say, what is the fewest number of things that you can do this in? 7. Great, there's my answer. Other times it might say, what is the fewest number of things you can do this in, and which ones are they? Now that's where current best, that's where update may have to do different amount of work depending on a different problem that's offered to you. All right. We've got this other thing too, this lower bound. Now this starts to make sense that we talk about branch and bound because backtracking was all about investigating branches. So we see where the branch comes from, but the bounding is where we talked about this estimating of a solution, right? And the estimate of a solution takes a partial solution, which we can always measure. So if I've got to connect these 25 cities in my TSP, I say, well, I've got these 5. Well, I know the exact path through those 5. I can measure that path. So that's the cost so far. And then I've got to estimate what it's going to cost me to connect the other 20. So the lower bound ends up being the combination of the cost so far, the actual measurement of the 5, plus the lower bound estimate of what's remaining. The underestimate is important here because I want to underestimate. It's okay if I'm wrong and I haven't given enough. It's not okay if I'm wrong and I said too much. And here's why. Let's go back to our early simple example. I've got a current best of 40. If I've walked down this pathway and I'm halfway there and say, well, this particular route has taken me 20 so far, and I estimate that the rest of the work is maybe 10 or 12 more. You're like, well, hey, if I'm at 20 and I go 10 or 12 more, then that looks like I could possibly have a solution that's a 30 or 32, which would be better than 40. I'm going to investigate this path. It looks like a good one. So if I said it was 30 and it turned out to be 32, and I investigated because I thought it was 30, I would still find the 32 and be less than 40. That's good. Now imagine that my estimation function wasn't quite as good. So I'm on the same partial path, I've gone 20, and I know that the ultimate answer, I know, not while I'm solving this. Without solving, I don't know. So it turns out that it's 32, but if my estimate says, well, we think it's going to take you another 20 or 25 to get there. So you say, well, I've gone 20, and if I go 20 or 25 more, that's 40 or 45. That's not better. I'm not doing it. I'm not even going to check because that's a waste of my time. So if the answer was actually 40 or 45, I would have pruned appropriately because it's not better. However, if I overestimated and said I think it's 20 or 25 when it's really just 12, I don't go that way and I quite possibly miss the optimal solution. So that's why this has to be an underestimate of the remaining work, right? Because I'm trying to do this minimization, so I have to have an underestimate. So if I overestimate, yes, I have the very real possibility of saying, well, let's not even try that, even though the right answer is down there. So you would over prune, you would prune the optimal solution because your estimate was on the wrong side of good. So an underestimate is good because, remember, it's okay to have the wrong answer if you end up shorter. If I thought it was 30, but it really is 32, and 32 is better than 40, I get there. If I thought it was 50 and it's really 32, I didn't go there. So promising then is different for each application, but it has to return true when my lower bound is less than my current best, as well as, we can't violate any constraints. But if my lower bound looks like it's less than my current best, that means I should try to extend that solution. False value causes more pruning when we're talking about greater than or equal to. Because remember, we're trying to find an optimal solution. I don't need 2 optimal solutions. So if I've already got a 40, if this one looks like it's 42, I would still prune it. There's no sense doing the work to find another 40 because that's just unnecessary work. We're trying to get speed here. And so if speed says prune something that's not better than what I have, I'm okay with that. The key, of course, to branch and bound is the bounding part. It's what makes it not be backtracking. So the efficiency of this pruning comes from whenever I can prune, the better. So the more I can bound away because I'm saying this estimate is bad, or this estimate says this trip looks bad, the more I can prune, the faster my search gets. The more unpromising partial solutions I don't have to look at, the faster I get done. So the earlier I know a solution is not promising, the less time I waste. This makes it important that I can get to accurate computation of partial costs. Now, hopefully you're scratching your head at this point, saying, how do I guess what this is going to be? Similar to my problems with backtracking, that's the hard part of branch and bound. How do you find a way that does a reasonable estimate of what work is left? And it's a special reasonable estimate, right? Because that reasonable estimate can never be wrong on the long side. It can be wrong on the short side, but it can't be wrong on the long side. How do I do that? Sometimes it ends up being worth spending some extra effort on this. So you might say, well, it takes me quadratic time to see if this estimate is working. Like n squared, I got to do n squared work a lot of times. Well, if doing n squared work saves me from doing factorial work, you dive on that. So it's worth spending a bit of extra time down here calculating what this estimate looks like, because if this estimate can prevent me from doing factorial work, I'm willing to take it. Optimization generally has two forms, right? There's the minimization, that's one way to optimize, and there's a maximization. So what we're doing with TSP is a minimization. We're trying to find the minimum path there. So this is how we're going to do it. We've got the opposite though. When we start talking about branch and bound, I can still use branch and bound to optimize for maximization. So if I do minimization, I might start with some infinity bound, meaning that anything that's better than infinity, anything that's shorter than infinity sounds great. I'm trying to minimize here. Just like when you're trying to find the smallest value, you start with a max and then say if it's less than what I've got, keep that. If it's less than what I've got, keep that. If it's less than what I got. So I'll start with some infinity bound, and then I can find my first complete solution. That's another way to do it. You can either start with an infinity bound and say anything that beats this I'll take. So eventually you'll find one solution. Once I've got a complete solution, no matter how good or bad it is, that's my new upper bound, because I'm unwilling to say I will look at anything that's going to cost more than this because I already have this. This is already a solution. If I can't find something better than this solution, then it's the best. Let's throw everything else away. So there's my new upper bound as soon as I've got a solution. If I find another solution that's a little shorter, I lower my upper bound and I lower my upper bound. Every time I see something that says, well, it looks like it's going to be here, throw that away. If I find something better, then I lower my upper bound. Find something that's going to be up here, I throw that away. I lower my upper bound. When I get done, my upper bound, that's the answer. Right? That's the shortest that I could find. So that's the way minimization works. You've got to have this estimate, and it has to be an underestimate with minimization. Let's flip this around. What happens when I maximize with B&B? We won't be doing this in Project 4. You start with a zero bound now, because anything that's better than that is going to be bigger than zero. So if I find my first complete solution, now this is my lower bound, right? Anything that falls below my lower bound is not obviously my maximum. So if I find something that looks here, it's not high enough. You haven't reached the bound. The bound is here. Anything below the lower bound gets pruned away. Now, if this ends up here, that's great. I've got a new maximum. So maximizing with B&B, you just take all of the language that we use in minimizing and flip it. You've got upper bound, lower bound. When we finish a minimization with B&B, our upper bound is the solution. When we finish a maximization, our lower bound is the solution, right? We start with infinity on minimize, we start with 0 on maximize. All the same, don't dwell on it too much. I just want you to be sure that you understand that I can maximize with B&B, and it doesn't require me flipping everything around. It's complicated enough to understand B&B, so this is the last we want to think about maximizing with B&B before we get done with P4, because P4 is going to make sure that you really get into how to minimize things. Here's my B&B summary. This is a way that I can prune my search space for optimizing. I keep my current best solution, and I use that as sort of like the watermark test to see, well, if you're going to not be better than that, I don't even have to do this work here. I sort of measure partial solutions, and then I find some optimistic estimate, and I combine my partial solution with an optimistic estimate, right? So optimistic means I'm underestimating while minimizing. Optimistic means, hey, this might be huge. When I'm maximizing, that's good. So overestimates are good when you're maximizing. Underestimates are good when I'm minimizing. So I need to have some optimistic estimate there, and then I figure out that if my estimate and partial isn't an improvement, then prune it, because if I'm sort of looking at the world with, you know, through these rose-colored glasses, this is going to be great. If it looks like it's going to be great and it still fails, then it's just a fail, right? So that's where it says, if my optimistic estimate still isn't good enough, the reality might be that my optimistic estimate is wrong and the reality is even longer. So if my optimistic is bad, then my actual would probably be worse. That's why the underestimate is okay, because I say if my underestimate is too long, then the reality is going to be even longer than that. So why spend the time figuring out what that reality is? All right, there's branch and bound. Let's look at this even closer. TSP time. So in TSP, we're going to do a specific application of branch and bound. So we'll get to see what promising means. We'll get to see what solution looks like, right? So here's TSP. Start with our first definition. We have what's known as a Hamiltonian cycle. And if I've got some graph G with V and E, what I want to do is find a cycle, means start here, go places, end up here. I want to find a cycle that starts here, goes through all the places, but never goes through any place more than once. This is from people who used to earn a living selling things. So if you're driving, you're not selling. So if you drive from here to there, you're not selling in between, but when you get there, you can sell. You don't want to have to go back through some place that you've already sold at to get to another place. That's just wasted time driving, and you've visited places that you don't do any selling at. So the Hamiltonian cycle says, let's find this path that starts here, goes through all the places, ends up here. That's a constraint satisfaction problem. Start at this location, visit all the other locations, that's a constraint. Don't visit any location more than once, another constraint. End up here. There it is. That's a constraint satisfaction problem. The TSP says, well, can you do that and find me the absolute shortest route? The Hamiltonian cycle with the least weight, an optimization problem. I want the minimized path weight. So this is where TSP going to use this. So here's a pretty simple one. You can do a simple examination of this small graph. It's got 6 points, sort of a hexagon with a point in the middle, and everything is connected around this sort of spoke. So this F vertex is in the middle, is connected to everything, and then we've got this loop around the outside. So if I'm trying to use this one and come up with what my tour would end up as, I can see that I've got to get into F. If I start on the outside, let's say I start at A, call A home base. If I start out on the outside, I've got A, B, C, D, and E around the outside with F in the middle. I've got to get into F. How many times? Not 0, not 2 or more, just once. So, because I can only go through each vertex once. So if I'm trying to find a way around these 5 points on the outside, I've also got to jump in once and then back out. So you can sort of figure out what that looks like. It looks like me sort of removing one outer edge because I was taking time to dive into the middle. And what you might do by looking at this by inspection, you say, well, I've got this one edge on the outside, this AB edge of weight 9. That's the heaviest edge in the entire graph. I might find a good solution to this if I could prune that one out. It turns out that's actually the optimal solution here. So if I go to A, jump into the middle of F, then B, C, D, E, and back to A, that's a solution. If I want to go the other direction, I can go A to E to D to C to B, in the middle of F and back out to A. That works as well. So this is it's always good when we're trying to find something to know what the answer that we're trying to come up with looks like. So you can see here that if I cruise around, cut into the middle, travel A to E, E to D, D to C, D to C to B, BF, A, then I end up with something that looks like 9 or 8, 17. There's a 20 weight path, right? 20 weight path that goes around here. So my optimal solution for this is a path of weight 20. As we look at TSP over the years, we see that in 1954, the state-of-the-art competition-winning TSP solver was able to pull up about 49 different vertices. This is a trip across the United States. 50 years later, with much more computing power, we've got this trip through municipalities in Sweden. Looks like about just under 25,000 of them. So this constituted many hundreds, thousands of computing hours, but a solution was able to be found here. So this is the state of the art. If you go to the website given here below at Waterloo, there's a whole page that's dedicated to the TSP, the history of the TSP, some of the algorithms that are used. There was one on there that I think that was like 80,000 points on a circuit where transistors would be located. There's another TSP solution. So here's TSP with backtracking. Back to that graph, we've got A, E, D, C, B, F. So if I were just to use backtracking, and what backtracking does is says, let me start at A and find if I can get to A again without having run into any point more than once. So with backtracking, I only prune when I violate a constraint. So you'll see I can go A, B, C, D, E, F, A, no problem. A, B, C, D, F, E, A also works. That's just me cutting in a little bit earlier. As I keep going, A, B, C, F, D, E, A, that's a full way to get there. But now I can work myself in a corner when I start out at A, go to B, go to C, jump into the middle, go to F. Then if I go across to E, I've got to either go to A or D, but I can't go to both, because if I go from E to D, that works me into a corner where I can't go to A without visiting some other city twice. So that's an unpromising partial solution. All the adjacent vertices to D have been visited, so I end up pruning this. Not a lot of savings here, but you can see where all of the ways that I can get through this decision tree. I've got A starting at the first level, all of my second level decisions. A can only go to B, E, or F. Everyone has their limited number of places they can go after that, and so that's what this decision tree looks like. And this enumerates all the possible ways that backtracking can find a solution for me for this TSP. Now let's add B and B. Let's add the branch and bound. So what the branch and bound is going to do is start saying I'm going to prune when I get part way. So we're going to have a little bit of a leap of faith here. We know that if I just truck around the outside, A, B, C, D, E, F, A, that's going to be a weight 27 path. So that's good. That's a good place to start. If, as far as I know, when I go A, B, C, D, E, F and get there in 27, that's the best I might ever find. So I'm going to keep that, say that's my best so far. Now, the next branch that I investigate, A, B, C, D, F, that costs, A, B, C, D, F costs 23, which is still good. It's better than 27. But now I know, because I can just use this graph in particular, it's small enough and simple enough that the remaining work, if I go A, B, C, D, F, to get from F to E to A is going to add 8 more work. So it'd be 23 up to F, and then 8 more. If I had some function that would tell me, I think it's about 8 more from here, then I would say, well, why would I go farther then? I've got a 27, it's costing me 23 to get here, and I think there's 8 more. It's going to be way over what I've already got. So pruning happens there. Farther up, you see the next branch that we go back, A, B, C, F. I can get there in 22. A, B, C, F is 22. If my estimator says, well, to get the rest of the cities connected, that's going to cost 9 more, I say, well, 22 plus 9, that's 31. That's not better than 27. Let's just prune it here. 22 is a bad way to get through these 4 cities. If it's taken me these 4 are taking me 22 already, it's not going to be good. Here's an equality prune, right? A, B, F, C. A, B, F, C, I can get there in 21. If I add 6 more, which is about the work that it would take, I would end up with a 27. 27 is not better than 27, so prune it. It's a waste of time. It's not the best. It's not getting me anything better. right? I get to some other dead ends here, A, B, F, D, C. I see I've worked myself into a corner. I've got some dead ends. I've got things that I prune because of weight, and I got things that I prune because it logically doesn't get me there. Now let's say I cut across from A to E. This is me coming down the middle branch on the decision tree now. A to E to D to C to B to F to A. There is one of my optimal solutions. The other one just goes the other direction in this particular graph. But this one has got a weight of 20 now, so I can throw away this 27 and say the best I've seen is a 20 now. That's good, I'm going to keep that. So as I get to that next branch that I investigate, AEDCF, I say, well, I get there in 14, and there's only 10 more work. That's 24. Back when 27 was the best I had, 24 would have been awesome. It's not anymore. So what we do is prune that as well. Same thing, AEDF, that's got a weight of 11 with an estimate of 9 more. That's a 20, but it doesn't beat the 20 I've already got. Why work on it? Prune it, prune it, prune it. And so you can see the earlier I'm able to prune, like that last branch to the right, it says, well, from A to F costs you 5. If you've got a magic estimator that tells you the rest of the work is about 15, then you would say, well, why even bother going that way? That's not going to be better than what I've got. So the earlier I can prune, the better I do. So the more accurate my estimator function is, the more likely I am to get something that helps me prune. So what I want this to be is always an underestimate. But for sure, I could just pick 0 all the time. That's an underestimate, isn't it? Sure, what does that do? It just says, well, everything looks good. Let's try it all. That makes me look like I'm exponential. Now, if I've got an underestimate that is absolutely as high as it can be, that's letting me prune more. That's what I want. I want an underestimate that is as large as possible. How do I come up with this? My bounding function I mentioned, the estimate has to be less than or equal to reality. It must have a complexity better than just doing the TSP, right? The rest of the work that I have to do for my K vertices, it's K factorial to try all of them in all of the different ways that I could do it in. So if I do some work that's maybe K squared or even K cubed, for instance, for a lot of K, K cubed is still far better than K factorial. So there is a little break-even point there, and you might be able to use that to your advantage in P4. Say, well, at this point, I can just say everything looks promising because it's more work to do the estimating than it is to just try all the versions, right? Because K is so small. So you'll do some thinking about that, and it starts with setting K squared equal to K factorial and figuring out what that K is. What method, when we're talking about graphs, now if I'm talking about this TSP, I've got some partial path that I know has everything connected in some particular order. Not everything. The items that I have already connected on a partial path, I've got them connected in some order. How might I connect the things that aren't connected? Cheaply. What's a cheap way to connect a bunch of vertices? Go back a few lectures. Cheap way to connect vertices. Right? Remember, we're trying to get an underestimate, and so if we've got the cheapest possible way to connect these vertices, even if it might not lead me to a legal Hamiltonian cycle, that's still okay. Because if the cheapest possible way to connect them is an underestimate because it would cost me more, if that cheapest possible estimate says, well, this is too long already, then I'm happy with pruning it. So, some vertices are connected, some vertices are not. We've got the innies, we've got the outies. For the unvisited vertices, the ones that aren't connected, connect them together with the lowest possible cost, and then connect those visited vertices to the unvisited vertices, and then I've got an estimate. So this might definitely give me something that doesn't look like a Hamiltonian cycle, but any Hamiltonian cycle that starts with the partial path I'm investigating would have to be longer if I found the shortest way to connect them. It would have to be longer, or at the very least, no shorter. And so that's okay that it doesn't actually look like a Hamiltonian cycle. It works. So here I've got a partial TSP example. See here I've got these 7 points, A, B, C, D, E, F, G. I've already got A, B, and C connected in that order. A connects to B, B connects to C. So this is my partial path, and I can measure those two edges, AB, BC. Add them together, that's my actual partial path weight. What I don't know is how much it's going to cost to connect the rest of that stuff, the D, E, F, and G. What's the best way to connect them together? I saw Benny hit it up. He said MST will do it. That's the cheapest way I can connect those 4 vertices to themselves. Sure, that's certainly not going to be wrong, right? It's not going to be long wrong. It might be long short. It might be wrong short. That's not going to be wrong long. So if I connect them all, now I'm still missing a couple of edges. And why do I know that I'm missing a couple of edges? I could use that as is as my underestimate. What's the problem with this as an underestimate? It's too far under. It's going to say a lot of things look good that really don't. So I'll investigate more items. So this is an okay estimate, but it's not great. Why do I know that I could go longer? Well, if there's 7 points, any Hamiltonian cycle must have 7 edges because I've got to leave every place once. So right now I've got A to B, B to C for 2 edges, and then D, E, F, and G are connected with 3 edges. That's only 5 edges. My fingers are counting for me. 5 edges. So if I could add 2 more edges and still end up with something that's shorter than the ultimate, then that would give me a higher lower bound estimate. So what do I need to do is make sure that everything gets connected. So far, A only has 1 connection and C only has 1 connection. That's a bad thing. So let me find a way to connect my current path to the things that aren't connected. And the way that I do that is find something. Let's find the shortest edge that I can use to connect A to anything unvisited. The shortest edge that I can use to connect C to anything unvisited. I only need to connect A and C, the beginning and end of my current partial path, because everything else in the middle is already connected. So this has only got 2 points, but if I had A to B to D, that's a bad letter. So let's put A to B to I to C. B and I would have 2 connections out of them already. I wouldn't have to worry about them. The only ones that I have to worry about are A and C, the beginning and end of my current partial path, because they are not connected. So let's find the shortest way to connect A. It turns out, because of the way that this graph is set up, A would connect to D and C would also connect to D. That's okay. This doesn't look like a Hamiltonian cycle at all. But any cycle that I have that starts out with A, B, and C has to be longer than this. That makes this a good underestimate. I can't reliably get a longer underestimate without going over using this method. So this is good enough, right? So what I've done is I've looped through D, E, F, and G and found the shortest distance to A. I've also, while looping through D, E, F, and G, found the shortest distance of one of them to C, and that gives me these 2 edges. So as we'll be talking about this in office hours, I've got the partial path, MST there in gray, and I call this other part the arms in blue. Those are the things that connect my current partial to the unvisited. So let's look at gen-perms. Here's gen-perms. We talked about it early on when we were talking stacks and queues. This version is a little bit more efficient. The stacks and queues version uses 2 containers and pushes things from one container to the next. This version is logically the same, but it's physically different. This does it all inside 1 container. So I've got this vector of things. That's my path, right? And I've also got this perm length that tells me how many of the beginning of them are in the permutation I'm concerned with. So for instance, as I'm developing this full path, if I got 10 vertices, when I start, my path has 2 things in it. then I say, well, if I go a little bit longer, I've got 3 things in it. So that's what perm length is. It says, well, the first 3, I'm actually using them in that order, and the remaining 7, I still have to permute a bit. So my current permutation length, or perm length, tells me how many of the things at the beginning of the vector are in the order that I want them in. When perm length equals vector length, then that says, here's a full-on permutation that I like. So the cool thing about this version of using branch and bound is the things that we talked about early on with backtracking and all of these constraints. If I take a vector that has all of my vertices in it once, and I never add any and I never remove any, I can't ever violate any constraints. I'm just putting them in different orders. So some orders are longer and some orders are shorter, but there's no way for me to visit, say, B, for instance, and then come visit B again because it's only in that container once. So in this case, promising here then just ends up doing to see, well, is this efficient? Is this going to be close enough to save me money or save me time, save me travel? So here's gen perms. You'll see it's a backtracking, right? Gen perms calls gen perms. We've got the things here that says, well, is this a solution? So if perm length is equal to path size, that's my base case of this recursive function. It gets me out. Because if perm length is equal to path size, I don't have to go in any further. I've got a solution. So now I need to do something with that solution. I might need to save it if it's better. If I've got a solution and it's not better, because it's possible to get to that very last vertex and have it sort of add more distance than you really wanted. And so I was good up until I added the last one. That's still, so just so I get to the end doesn't mean that I've got a good solution. So when I get to perm length equal path size, I have to do one last check to see, well, does this actually end up less than what I've got? Because if it does, I'm keeping it. So that's where it says do something with the path. Do something with means keep. If I don't like it, I'm done with it. Either way, I return. Either way I return because once perm length is equal to path size, it is no longer possible to extend the solution. I have already put all of the things in there that I could put in there. If I'm in gen perms and I haven't hit the end, now this is where in line 7 here, I say, is this current one promising? Because if it's not promising, what do? I quit just as well, right? This is me saying, well, I've got 10 points to put in there and I've already done 7 of them, but this is a fail. So don't try 8, 9, and 10. Return. That's what the for loop here. The for loop here is for extending the solution. Let's see if we can add more to this. So what it does is it goes through all of the remaining items, starts at perm length and goes to the end of the path. All of those things are the ones that aren't unpermuted, and says, well, let's try them in this new position, right? So if I've got these 10 items that I'm trying to permute, say I've got these first 4 all permuted, I've got 6 left. I want to try this one in the 5th position, then I want to swap so that this one is in the 5th position, then I want to swap so that this one is in the 5th position, and then this one, and this one, and this one. So eventually I've tried all of the unused 6 items in the 5th position for the used 4 items. That's what the for loop does. The for loop says swap something new into this position, that perm length plus 1 position, and then into that perm length position, and then call it with perm length plus 1 because we're saying the permutation length has grown by 1. Once I get done checking that for good or for ill, I'm going to put it back. So you see here, this line 10 and line 12 are the exact same line that says swap something new into this 5th position, and then swap it back to where it belongs. Then swap something else new into this 5th position, swap it back where it belongs. Swap something new, swap it back. That's how gen perms works. It's complicated, but you need to understand it. I would start with this, write a promising function that just returns true all the time. Print out what you see in path from 0 up to, but not including perm length, and you'll see the solution grow. Just put that first line in gen perms, just write a loop to print however many things are in perm length, and you'll see them, and you'll see it grow. It'll go 1, 2, 3, there's a 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, so on. So if I got 5 items, it'll go 1, 2, 3, 4, 1, 2, 3, 4, 5, and then it'll backtrack and say 1, 2, 3, 5, 1, 2, 3, 5, 4. And then it'll backtrack again, it'll say 1, 2, 3, 1, 2, 4, 1, 2, 4, 3, 5, 1, 2, 4, 5, 3, and then it'll backtrack again. So if you can have GenPerms print out enough for you so that you get a feeling for how this works, it will really, really help how you do for Project 4. Optimal TSP with B and B. So we've got these n vertices. I need to find the best path out of n minus 1 factorial options, right? I don't have to do n factorial choices because I know where home base starts. You don't have to permute position 0. That's where you start. So don't do n factorial work when you could do n minus 1 factorial work. What this means is you're going to call GenPerms, and you never want to say GenPerms, well, I have a 0 permutation length, because I know that at position 0, if that's in the first position, that's where I want it to stay. So I'm going to say that I always know that there's 1 thing there. So start GenPerms with a 1, not a 0. We'll start with some upper bound that's infinity, or better yet, a fast calculation of a path that's guaranteed to be not shorter than optimal. So if you're thinking here, I could use my fast TSP from part B. That's why we put part B before part C. You're in the know. You can use that as your first bound, right? You can use that as your first bound. Use that as your first upper bound. Then every time I go above that upper bound, I prune it. Every time I end up below the upper bound, I lower the upper bound. And I've got a complete path that's found, and I save that. Measure each partial solution. We know what the path length is to connect all the vertices that we know about. Then estimate connecting the rest of them. Prune if we can. If another path ends up shorter, save it and replace the upper bound. When I'm done, the upper bound is the shortest path. Whew. That's TSP. So here's the artwork. If you haven't had a chance to check out XKCD, I strongly recommend it. Lots of cool, fun stuff there. It's hilarious. It's very, very smart as well. This is someone using eBay. So the traveling salesperson here is trying to figure out how to work their way all across the country to find the shortest route. Brute force, we could get there in n factorial time. We're not doing the DP solution to this. It's a bit more complicated, and that's something that you might look at later on your own or in another class. But that version ends up being n squared times 2 to the n. And that's the most efficient way to get this done. And if you sit at home in your chair, that one location in constant time, that's how you do it on eBay. So that's what's funny there. And what else is also really cool about this is you do this splitting planes technique with that dynamic programming algorithm. And the splitting planes technique would actually divide the country kind of just the way that it is there. It looks like these are 3 different frames of a comic, but that is actually drawn in a way that the splitting planes technique would split the US to find those, to find that actual optimal path, which is why I say there's really smart humor there. The guy is an amazing engineer and scientist, and he's really funny as well. So check out XKCD. We can almost never get enough of them. So here's the N-Queens demo. I mentioned we didn't want to run out of time on TSP, so if you have to cut out before this gets done, you can always come back and watch the rest of the video. I am going to do the N-Queens video, or the N-Queens demo next. So we talked about the N-Queens, the way that we implemented it. We know that each row has exactly 1 queen, each column has exactly 1 queen, and each diagonal will have at most 1 queen. So if I can do that and look in each one of those in constant time, then I won't have to do these linear verifications of whether or not this is promising. So let's look at what my solution would look like. Here's one of my vectors here. I've got this position in row vector that tells me in the first row I put a queen in position 1, in the second row I put a queen in position 3, third row I put a queen in position 0, fourth row I put a queen in position 2, and these are all 0-based indexes. I apologize for the first, second, third. It's like 0, 1. But you see what I'm saying here. You can see how that solution where the queen in the first, or the first index, which is the second position, the first index of the first row, this 1, 3, 0, 2 represents my actual solution. So this is one thing that I will keep track of while solving the N-Queens problem. This position in row vector, it's 1 by n. And it's a collection of integers that tells me where each queen goes in that row. Here's another way that I keep track of it. I've got this n by 1 vector of Booleans. And this n by 1 vector of Booleans tells me how many columns I have that are still available. And we're back. All right. So I don't know exactly where that cut out, but what I was talking about is this 1D vector that shows me column availability. There's nothing in the first column, so I say that it is available. That's why that Boolean is a true. There's a queen in the second column, meaning no other places in the second column are available, which is why later when I go to place something in the third row, I can say, well, can I put this in the first column? And if I look in this vector in constant time, it will tell me, yes, this first column is available. If I look at the second position later on, I say, well, this column is not available. Move on with a constant amount of work. All right? So then lastly, I've got these two other diagonal checks as well. So these diagonals, now I've got more diagonals than I have rows and columns. We see we've got these what I call left diagonals, and a left diagonal starts at the upper left, and each one of those diagonals goes from down left to up right. So that's how left diagonals work. And that first one up there at the top left, that's the 0 diagonal. Then there's the 1 with the queen on it. There's a 2, 3 diagonal right through the middle, the 4 diagonal with another queen on it, and then 5 and 6 are after that. So you can take this vector here, and in the first position, it's got a true because that upper diagonal is unoccupied. So I can calculate any diagonal index. Where in this vector does it show up? If I add the row and the column, that tells me where it is. So that first queen in the first row queen in the second column, that's really index 0 for the row, index 1 for the column. If I add those together, it says check the 1 diagonal. And if I look into this vector here that's got a T for available in the 0 position, but a false for available in the 1 index, then that's exactly what I can do. I can check in constant time. I just have to add row and column, then look into this vector, and in constant time I can get whether or not that place is available. The right diagonals work similarly. They start at down right and move to up left, and we're going to start indexing at the upper right. We work our way down, and you can see here that those same queens now end up in slightly different right diagonals. The right diagonal has the queen on it in this position, and the way that I calculate the diagonal index is a little bit different when I'm calculating the right diagonals. I'm going to take row minus column, which of course might give me a negative number depending on my configuration. So if I add an additional n minus 1, that's like modding to get me back around the side of it. So I take and calculate my diagonal index in constant amount of time and then check to see if that diagonal is available. I can place these queens pretty easily. Here then is what promising is. Promising is given some row and column, I'm trying to say, can I place a queen in this place, in this position, in this row and column? Is that promising? Well, if the column is available and both the diagonals are available, then yes, it's promising. And that's all we have to do is we can look this up, and you can evaluate the statements in this. There's a comparison, a comparison, and a comparison. 3 comparisons, 2 conjunctions. This is constant amount of work. So I can tell whether any given row-column combination is a promising place to put a new queen. That's how this works. Whoa, more code. But look closely. This is put queen. The function put queen here defined in line 1 calls put queen here in line 15. We're getting to backtracking because put queen in line 15 is wrapped in this loop from 8 to the end of the function. So there's my solution extender. Here's my solution check in line 3. If row is equal to n, if I've placed a queen in the last row, I can say that a solution was found. This one just prints out the fact that a solution was found. It doesn't print the solution. It doesn't count the solutions. This is a real simple version. You can add more to it on your own. So this finds a solution and returns. In the for loop, you see that before I do anything, I'm using the for loop to try to place a new item in this current row. Because every time I call put queen, the one parameter that I get is row. I'm in this row. So in this row, I use the for loop to see where in the row do I place a queen. The for loop trucks through there. If it's promising, then I'm going to extend the solution that way. So if it's promising at that row and column, then I say, well, let's put something in that position in row value. I'm going to put that column. And I'm going to say that this column is no longer available. I'll say the left diagonal and the right diagonals are no longer available. And then I'll try to put queen in the next row. Just as before, I have to undo the work that I did. So after I put queen, I'm going to say, well, now let's make that column available again. Let's make those two diagonals available again, because this allows me to use that same set of these 4 vectors, 3 with Booleans, 1 with value. I can use those 4 vectors for all of my solutions because I make changes and I undo those changes later. Here's the N-Queens demo. Like I said, I know we're over time here, so if you need to cut out, come back and see where we're going through the rest of this. So I will jump over to Kane here. Hello, Mike? Hello, Mike. All right. Phooey. Okay. I'm back alive and unsound here. So you did get to see what I did there. I was able to download the code with wget. Then I did an untar. I took all the things out of the tarball, and I also did a compile and build. And it just gave me an executable end queens, and then I ran end queens from the command line. It asked me for a number of queens that I wanted to show. I said 4 of them. Do you want to display the results? If I said yes, it shows me these 2 solutions, and these are the 2 that we found as well during the lecture, or at least we found the one of them, and then the other one is just the mirror image if we want to flip this across either my horizontal or vertical center. But the program goes on and tells me that there were 60 branches explored out of 256 possible. We note that early on in the lecture we found our first solution after 19 branches explored. So it seems like after exploring another 41 branches we find at least one more solution. So in the end, after having only investigated 60 branches, that looks like over 3/4 of the work I didn't do. That's great. Still got that really large asymptotic complexity, but in reality here, I've got a savings that's pretty huge. Let's see if we can make this bigger. How about n queens 5? And sure, we'll still look at those results. N queens 5 gives 10 solutions. Ends up investigating 220 branches out of 3,000 or more. So there's 3,125 possible permutations. We look at 220 branches, find 10 solutions for a savings of nearly 93%. Let's go bigger. Always bigger. Let's look at 8 this time. Well, hold on before we do that. I'm going to scroll back through here. So we can see in the 5-queen solution, you can kind of see like one of the 4-queen solutions embedded there. We just sort of wrapped that up with an additional row and column and add a queen there that didn't cause any problems. As I scroll back, you can see a few other versions of just rotating that 4 and adding 1. This is a 5 only solution. This one wouldn't fit in 4 any way you cut it. So there are some unique ones, but there are 2 mirrored 5 only solutions, and then both of my 4 solutions have 4 rotations on them, and there's my 10 solutions. All right, let's try 8 queens, and this is maybe the last one we'll print. So if you want to scroll back and check out how you might do this before you start sitting down with your own chessboard, here are tons of them. How many of them? We said there was 16 million tries and 92 solutions, right? 16.77 possible permutations, 16.77 million possible permutations, and that gave us 92 solutions after investigating a mere 15,720 branches. This is now a savings of 19.9%. That's impressive, but we're not stopping there. How about n queens of 10? And no, we're not going to print those. It gets done here and says we found 724 solutions after looking at 1 times 10 to the 10th, right? Now we're talking 10 billion possible permutations. We looked at almost 350,000 branches, savings now upwards of 99.99%. Oh, we're not stopping though, because we've got computers. So 12, oh, I said yes. I did not want to say yes. It's going to take longer to print all of these things than it takes to calculate them. So let's just do this with 12 and no. All right. Can't hear anything? What? Oh, that's good. That's just an old one. I'm like, this has got to be on now, right? Has it not been fixed? Ah, I see my VU meter working over here. Somebody let me know that this is audio not working. Still no audio? Oh, okay. All right. Panic down. All right. Good. All right. So now I got to reorder my windows. There we go. So here at 12 queens, it looks like I've got a savings of 99.9999%. That's amazing. It would have been 8.9 times 10 to the 12th, right? 8.9 times 10 to the 12th, that's 8.9 trillion possible permutations. And we went through and investigated 10 million branches to find 14,200 solutions. Let's not stop. Let's go to 14. Definitely not printing all of those. Look at there. There was our first hitch. You saw I hit enter after the no, and it paused for about a second. There were 1 solutions. 0 branches were explored out of a possible 1 permutations. Wow. Looks like we've gotten some overflow here. I don't know how that happens. It didn't used to happen that way. 13. No, don't print. Oh, crap me. 13. No, don't print. So somewhere between 13 and 14, it looks like we got ourselves an overflow. The good news is, though, up there around 13 or so, this algorithm becomes flawless. We see that we've got a savings of 100%. It means this was free, and that's obviously not true. What we've got there is some floating point rounding error. But rather than checking out 3.0 times 10 to the 14 permutations, we found these 73,000 solutions by only looking at about 59 million of them. Let's try that. So we said n queens, the number of queens should be 14, and no, we don't want to return the results. Aha, there we go. Thanks, Benny. Was that you, Benny? No, that wasn't Benny. All right, but what do we see? Now I've got 14 solutions, and if there was a little hitch there. After I hit enter on the no, it paused because it's starting to do that much work. How about trying a 15 and no? Now we see an even longer break here. This 15 and no displaying of the results is going to take 20, 30 seconds here, and it'll give me the answer. Come on. Come on. The 16 takes multiple minutes here. So here we see why by doing an n queens of 15, it's 4.3 times 10 to the 17th possible permutations. We found, we investigated 2 billion branches and found over 2.2 million solutions. So this is really how efficient this can be. So if you're concerned about this, this is the kind of thing that you should run and try. I had people asking me, well, what about the memory used in all the stack frames? Apparently, this is a lot of work that still gets done with a reasonable number of stack frames. We haven't had a stack overflow. It's just me typing the wrong things. So like I said, I would run 16, but it's going to take minutes and minutes. And 17 would take much longer than that. But that's the n queens demo. Pull that code down and check it out. Here's my driver. All it does is take some input, and then it creates an object of n queens type. Gives me an n queens object with a particular board size, asks me if I want to display anything, and then does the running. Uses a couple of getters to see how many solutions were given and how many branches were tried, and does a little bit of calculation to tell us what that savings was. All right, if I want to grab nqueens.cpp, you can see many of the things that we've already looked at. Here is the promising that I wanted to deal with. I've got check the column and check the 2 diagonals. That's good. Here's solve. All solve does is try put queen, and put queen is my recursive backtracking function. So here's backtracking. We've got put queen, calling put queen in row 58. Check for row equals size. That's my solution check in row 40. And here you see when we have a solution, we have to do something. In this case, we're trying to count all the solutions, and we're trying to print the solutions if we were asked to. So that's what's going on there. You might have to add something up. You might have to store one of these particular solutions. In this case, it just prints them all. But if you wanted to save the best one, you might do something different there, right? And the rest of it was just as we looked at. Every time we go through the for loop on the outside, that's one of our branches tried because we found something that was not promising. That's the n queens demo. A little bit over time, go back, check this out, and absolutely, absolutely spend some time with this code. Even if it's just fun to read how somebody else writes. This was written by Dr. P. It's very much in his style. Our styles are very similar. We've been programming near each other as friends or colleagues for about 25 years. So we've got a lot of things that are similar, and then we try to do things the same for class as well. So you'll see most of my code look like this as well. But just having a chance to read indentation, comments, structure, ordering, all the things that are good things to know about code. And you can see here, this is where the nifty ASCII generation of the boards shows up that actually prints the queen boards out. That is the N Queens demo. All right, folks, lunch is late. I apologize, but let's go eat.